So good evening, everyone. I thank the organizers for this valuable opportunity. I'm going to talk about phase separation of fluids in confined geometry, partial and complete wetting. I've done this work with my PhD supervisor, Dr. Bhaskar Singh Gupta. So we start by asking, what is phase separation? So we have seen many examples of phase separation in our day-to-day life in front of us. So that is water and oil, or oil or vinegar example, all these phase separations. So phase separation is basically the creation of distinct phases from a single homogeneous mixture. So why do phase separation happen? This is a scientific reason. So this is a phase diagram of free energy profile for the phase separation. We can see at high temperature, the homogeneous phase is stable with the minimum of free energy. But when suddenly the system is quenched below the critical temperature, the free energy curve changes and the free energy is not minimum anymore, and then the system becomes unstable. So for stabilizing the system and minimizing the free energy, the system starts to phase separate into A-rich alpha phase and B-rich beta phase. And this kind of free energy curve favors like particle interaction more than cross particle interaction. So we implement this into computer simulation with cross particle interaction to be weak and a very strong like particle interaction. So this video is a typical example of phase separation of binary fluid in a three-dimensional bulk system. So for the kinetics of phase separation, it is important to analyze the domain size. And domain size is nothing but the size of the domain whose time dependence is given by L of t approximately equal to into time to the power alpha, where alpha is the growth exponent. We calculate this by starting with the order parameter, which is the local density fluctuation, which we can calculate by mapping our system equivalent to the Ising model. And the phi value can be +1 or -1 depending on the dominance of A or B particles. And next, from the order parameter, we can calculate the correlation function. And the correlation function decays with distance moving from one domain to the another. And the first zero crossing of the correlation function gives us the domain size for the corresponding time. Then when we plot this domain size as a function of time, we can get the domain growth of the system, which is initially having a diffusive growth, and it is given by the Lifshitz-Lozow law, which is the growth rate of t to the power 1/3. And later, when it goes to the viscous hydrodynamic growth, it is having a linear growth. And later on, theoretically, we expect a late time growth of inertial hydrodynamics also, that is t to the power 2/3. But in bulk systems, because of finite size effect, we rarely observe this. But this is all about the bulk system, but rarely we see this bulk, but this is a very well studied systems and very well comprehended. But what we are going to see is what happens if the system is confined instead of bulk. So we categorize the phase separation confined geometry into two, that is simple pore. First is simple pore, where the binary fluid is confined inside the cylindrical pore and with no interaction with the wall. The system will be having plug-like domains and the metastable state is obtained. So no matter how long we wait, the full phase separation is not possible. Then the next one is complex topology, where the bicontinuous porous structure is acting as a confinement for the binary liquid, which is not having any interaction with the confinement. Here also the domain growth slows down and the domain size is dependent on the pore size. Now, one thing common for all the confined geometry systems is that there is no interaction with the wall. That is, the wall is completely neutral towards the liquid. So what we are going to do is, our motivation for the work is that what happens in a real system where the fluid interact with the container? Will there be a partial or complete wetting? So this is what we are going to focus in our study. Phase separation in a cylindrical pore with an interaction with the confinement. So our main objective is to find out whether it is possible to break the metastable state that we have early observed, and even if so, is it possible to achieve the full phase separation? So we are going to analyze both the partial and complete wetting scenarios. And here we see the wall structure, which is having a length of L and a diameter D. The length will be very, very greater than the diameter, and the binary fluid will be confined inside this cylinder. And the A particle will be having an attractive interaction, whereas B particle will be completely neutral towards the wall. So this preferential attraction of A with the wall will create a surface tension of A with wall to be comparatively lesser than the other type, which will pave way for the partial or complete wetting scenarios. So this is the standard interaction potential that we are implementing between fluids as well as fluid and wall. So we start by the partial wetting with a lower fluid wall interaction. We see for the lower values of the interaction, the domain formation is almost similar like that of the non-wetting interaction, that is plug-like domains are forming with sharp interfaces. But when we corresponds to the much higher values of fluid wall interaction, we see that there is a strong interplay between the phase separation as well as the wetting, and more particles are interacting with the wall, and the domains are becoming more distorted and deviating from the metastable behavior. So again we see the different final configurations for different wetting strength, and we can clearly see that the domain size are increasing with corresponding to the higher values of interaction strength, and also more particles are interacting with the wall, and the domain boundaries are becoming distorted compared to the sharp domain boundaries, which we can see for the lower values of epsilon. Then we start by calculating the order parameter and correlation. Because of the geometrical confinement, since the stripe has been formed, we calculate the order parameter and correlation along the axis of the cylinder by dividing the cylinder vertically into equal width, and the correlation also one dimensionally. So when we plot the correlation with respect to the scaled length for a particular interaction set, we get a very well data collapse, a perfect data collapse, and this determines the self-similar nature of the domains irrespective of time. But when we plot the correlation with respect to different interaction strength, we see that for higher values of the interaction strength, the scaling behavior is being violated, that is the deviation from the metastable behavior. And also when for x by L greater than 1, we see that the domain data collapse is completely vanished, and the change in domain behavior is completely different for different interaction strength, which has broken the self-similarity of the nature. The further structure of the system can be investigated using the structure factor by taking the correlation of the structure factor, which is according for large scale limit, S of kt is approximately equal to k to the power minus d plus 1, where d is the growth dimension. So for lower values, it follows k to the power minus 2 corresponding to one-dimensional growth. But for higher values, we can see that it is deviating from the Poirot law behavior of one dimension. And also there is, for lower values, there is a second peak corresponding to KL to the power KL approximately equal to 10, which is the domain boundaries which we saw for lower values of epsilon. But for higher values, we can see that the peak is almost vanishing, because as we have seen in the final configuration, the domain boundaries are no more sharper, they have been completely distorted. So for further quantifying the domain growth, we can see the domain size is here the average size of the stripes, and then initially it grows with a diffusive growth law corresponding to t to the power 1 by 3, and later on towards the hydrodynamic, it grows with a growth rate of t to the power 2 by 3, since the domain size is comparable to the system size. And also we can see that with the saturation that the domain size is increasing with the interaction strength. So from this domain estimation and the structure factor we calculated, we can analyze that the 0.5 is almost the close proximity of critical transition value. So the next epsilon onwards, we can see the metastable state is broken and a complete phase separation is obtained in the system. So when we see the time evolution, we can clearly see that for the red species is having a surface enrichment, whereas the blue species is completely expelled from the surface. So we are calculating the correlation radially outward from the center of the cylinder, and the correlation is also perfectly scaled for all the values of epsilon, which corresponds to superuniversality and the Poirot law. Here we calculate correlation separately for different type, and when we calculate the structure factor as from the Fourier transform, we see for type A, we are getting a Poirot law of k to the power minus 3 corresponding to the two-dimensional growth, which we can clearly see from the cross section that the system is, type A particle is growing like a two-dimensional curved surface. Whereas when we correspond to type B, we get a Poirot law behavior of k to the power minus 4 corresponding to 3D growth, which is like the bulk, it is like a bulk system. Type B is growing inside this along the axis of the cylinder like a bulk system. Now further analyzing the domain growth, we get for the type A particle, it is having a growth rate of t to the power 1 by 2 corresponding to two-dimensional viscous hydrodynamic growth, and for type B particle, it is having a growth rate of linear domain growth, that is three-dimensional viscous hydrodynamics. With this all growth rate also completely enforces the structure factor Poirot law behavior, which you have already seen. So this is the summary of the work that I've already just discussed. I especially acknowledge my soft condensed matter group, my supervisor Dr. Bhaskar Gupta, my lab members and my past lab members. Thank you.
Thanks, Daniya.